Section 29 of Great Men and Famous Women, Volume 6. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Great Men and Famous Women, Volume 6, by Charles F. Horne. Dr. Louis Pasteur, by Dr. Cyrus Edson, 1822 to 1895. Louis Pasteur, the Columbus of the world of the infinitely little, to quote the phrase of Professor Dumas, was born in the town of Dole, France, on December 27th, 1822. His father was an old soldier, decorated on the field of battle, who, after leaving the array, earned his bread as a tanner. In 1825, Monsieur Pasteur moved from Dole to the town of Arbois, on the borders of the Cuissance, where his son began his education in the communal college. The boy was exceedingly fond of fishing and of sketching, and it was not until he reached the age of 14 that he began to study in earnest. There being no professor of philosophy at Arbois, Louis Pasteur moved to Besançon, where he received the degree of Bachelier et Lettres, and was at once appointed as one of the tutors. Here he studied the course in mathematics necessary for admission into the École Normale in Paris, which he entered in October 1843. Already his passion for chemistry had shown itself, and he took the lectures in that science delivered by Monsieur Dumas at the Sorbonne, and by Monsieur Ballard at the École Normale. It was but a short time before he became a marked man in his class, especially for his intense devotion to experiment. Thanks to Monsieur de la Fosse, one of the lecturers of the École Normale, his attention was turned to crystallography, and a note from the German chemist Mitscherlich, communicated to the Academy of Sciences, set him on fire with curiosity. Mitscherlich declared, the para-tartarate and the tartarate of soda and ammonia have the same chemical composition, the same crystalline form, the same angles, the same specific weight, the same double refraction, and the same inclination of the optic axes. Dissolved in water, their refraction is the same. But while the dissolved tartarate causes the plane of polarized light to rotate, the para-tartarate exacts no such action. Pasteur at once instituted experiments resulting in the discovery of minute facets in the tartarate which gave it the power noted. He found in the para-tartarate these facets existed, but that there was an equal admixture of right and left-handed crystals, and the one neutralized the effect of the other. He also discovered the left-handed tartarate. These discoveries, at the opening of Pasteur's career, brought him at once to the front among the scientific men. He followed them with a profound investigation into the symmetry and dissymmetry of atoms, and reached the conclusion that in these lay the basic difference between inorganic and organic matter, between the absence of life and life. Nominated at the age of 32 as Dean of the Faculté des Sciences at Lille, Pasteur determined to devote a portion of his lectures to fermentation. At that time, ferments were believed to be To quote Liebig, nitrogenous substances, albumin, fibrin, casein, or the liquids which embrace them, milk, blood, urine, in a state of alteration which they undergo in contact with air. Pasteur examined the lactic ferment and found little rods, 1 in 25,000ths of an inch in length, which nipped themselves in the centre, divided into two, grew to full length, and divided again, and these living things he declared to be the active principles of the ferment. He made a mixture of yeast, chalk, sugar, and water, added some of the rods, and got fermentation. He then made a mixture of sugar, water, phosphate of potash, and magnesia, and introducing fresh cells, fermentation followed. Liebig's theory of the nitrogenous character of the ferment disappeared when fermentation was caused in a mixture having no nitrogenous elements. Pasteur had discovered that fermentation was a phenomenon of nutrition. It followed the increase and growth of the little rods. The next step was the discovery of the ferment of butyric acid, a species of vibrio consisting of little rods united in chains of 2 or 3 and possessed of movement. He found these vibrios lived without air. Further experiments showed there were ferments to which air was necessary, called by Pasteur the aerobics, and others to whom oxygen was fatal, the anaerobics. He proved also, by an exhaustive series of experiments, that what is called putrefaction of animal matter is the result of the combined work of the aerobics and the anaerobics, which reduced the part not taken up by oxygen to dead organic matter, ready in its turn to form food for living things. His attention having been turned to the needs of the vinegar makers of Orléans, Pasteur began the examination of the ferment which produces vinegar from wine. He found this in the Mysoderm aceto, a mold-like plant which has the power of developing acetic acid from alcohol. As the result of his investigation, the manufacturers of vinegar in France were able to do away with the cumbrous process that they had long followed, and to make vinegar not only more cheaply, but of very much better quality. But during these experiments, Pasteur found the temperature of 65 degrees Celsius was sufficient to kill the Mysoderm. When then the winemakers of France appealed to him to investigate the diseases of wine, he was ready for the work. Before this, however, he had examined the claims of Pouchet and others to their alleged discovery of spontaneous generation, in other words, the production of life. Ranging himself against them, Pasteur showed their experiments not to have been conclusive, simply because they had not succeeded in excluding the dust which contained germs of life in the shape of spores of microscopic plants. The diseases of wine produce sour wine, wine that spirits, greasy wine, and bitter taste. Pasteur found each to be due to a different microscopic ferment, all of which could be killed by heat. He placed bottles of wine in a bath heated to 60 degrees Celsius, and invited the most experienced wine tasters of Paris to try them afterwards. The result of the test was the unanimous verdict that the wines had not been injured in the least, and today these diseases of wine are a thing of the past. There are departments in France where the culture of the silkworm is the principal industry of the inhabitants. In 1849, a strange disease called pébrine broke out among the worms. They were unable to molt and died before the cocoons were spun. It spread in the most alarming manner until, from a crop with an average of 130 million francs a year, the production of silk went to less than 50 millions. The silk cultivators sent for eggs. Seed is the technical name, to Italy and Greece, and for one season all went well. The next, the plague was as bad as ever. More than that, it spread to Italy, Spain, Greece, and Turkey, until Japan was the only silk-producing country where the worm was healthy. Societies and governments, as well as individuals, were aghast, for the silk industry of the world was on the verge of annihilation, and every remedy the mind of man could conceive was tried, only to be rejected. In France alone, the loss in 1865 was over 100 million francs. At the suggestion of Professor Dumas, the government induced Pasteur to examine into the disease. He had seen in a report on the epidemic made by Monsieur de Quatrefages that there were found in the diseased worms certain minute corpuscles only to be seen under the microscope. When in June 1865 Pasteur arrived in the town of Alais, he found there corpuscles without difficulty. He traced them from the worm to the chrysalid in the cocoon, and thence to the moth. He found worms hatched from the eggs laid by these moths invariably developed the corpuscles. He crushed the corpuscular moth in water, painted a mulberry leaf with it, fed it to a healthy worm, and the corpuscles developed. He hatched eggs from moths free from corpuscles and secured healthy worms. While working on the disease, Pasteur discovered in 1867 that the mortality among the worms was in part due to another disease, the flacherie, and this he found was the result of imperfect digestion. Flacherie was contagious and was caused by the fermentation of the food eaten in the body of the worm. The causes of this fermentation, the condition of the leaves, the temperature, and others were pointed out. As the result of 5 years' work, Pasteur had restored the silk industry to its former position, and had shown that the microscopic examination of the moth laying the eggs to be hatched was a perfect safeguard against pébrine and flacherie. At the request of the emperor, Pasteur went to Villa Vicentia in Austria, belonging to the Prince Imperial. For 10 years the silk harvest there had not paid the cost of the eggs. Although he was just recovering from an attack of paralysis brought on by overwork, Pasteur travelled to Austria, introduced his methods, and the sale of the cocoons gave the villa a net profit of 26 million francs. No wonder it was said of him that his discoveries alone exceeded in money value to the French people the war indemnity paid by them to the Germans. Splenic fever, called charbon in France, had for many years decimated the flocks in France, Italy, Russia, Egypt, Hungary, and Brazil. It attacked the horse and cow as well as the sheep, and human beings died of it when they developed malignant pustule. Many scientific men had studied it, but Dr. Davesne in 1850 was the first to find in the blood of a sheep that had died of the disease little thread-like bodies about twice the length of a blood corpuscle. These little bodies exhibit no spontaneous motion. Pasteur began the examination of splenic fever by securing some of the blood from an animal dying from it. In the work before him he associated with himself Monsieur Joubert, one of his former pupils. A drop of the blood sown in the water of yeast, the medium used for cultures by Pasteur at that time, produced myriads of the rods, the bacilli or microbes. A drop of this taken at the end of 24 hours and placed in a fresh flask of the medium again produced thousands of the bacilli. Pasteur found that guinea pigs inoculated from the first flask developed the fever, and the same result followed when the inoculation was from the 20th. He had proved then that splenic fever was produced by the bacilli, by living organisms only to be seen with a powerful microscope. While working on the bacilli of splenic fever, Pasteur had isolated the bacillus of chicken cholera, had cultivated it, and had inoculated chickens with it, developing the disease. He found that so long as the cultures were made from flask to flask within 24 hours, the virus of the disease, that is, the power of the bacilli to produce cholera in the fowls inoculated, remained the same, and the fowl died. But he discovered that if a flask containing the bacilli were left exposed to the air for 2 weeks, and the fowls were then inoculated with bacilli from the flask, they became sick, but did not die. Following this up, he inoculated a hen that had recovered from a sickness so produced, with the bacilli in their strongest and most virulent form, and the hen showed no effect whatever. Then he took 2 hens, one fresh from the coop, and the other well again after the sickness produced by the inoculation, with the exposed bacilli, and inoculated both with the blood of a hen that was dying with chicken cholera. The first died, the second was affected. In other words, Pasteur had made the greatest discovery in physiology of this century. He had found it is possible to attenuate the virus of a virulent disease, and to use that virus so attenuated as a vaccine matter, which will guard the animal vaccinated against the disease. He had taken Jenner's discovery and proved it applied to other diseases besides smallpox. Pasteur's theory of the reason why a vaccine matter will have its prophylactic effect is this. He believes there is in the blood of any animal subject to a disease caused by bacilli some substance which is necessary to the sustenance of those bacilli. And when the bacilli, having an attenuated virus, are introduced, they slowly consume all of this substance. The substance being one which nature creates very slowly, no subsequent introduction of the bacilli, however virulent, can produce the disease until such time shall have elapsed that a new supply of the substance shall have been secreted. In this way he accounts for the fact that vaccination will protect from smallpox for a more or less defined period of time. Pasteur hastened to apply his discovery of the attenuation of the virus of chicken cholera to the virus of splenic fever. Here, however, he was met with a serious difficulty. The microbes of splenic fever, if left in the flask for 48 hours, developing bright spots, and gradually into these spots the bacilli themselves seemed to be absorbed. Pasteur found these spots were the spores or seeds of the microbes, and he also found that while the bacilli could be killed easily in various ways, the spores possessed a much greater resistance. They could be dried, for example, and preserved in that state indefinitely. It was apparent that the oxygenation which attenuated the venom of the bacilli of chicken cholera was impossible with those of splenic fever, if the bacilli of the latter disappeared within a week, leaving the spores behind. But Pasteur had discovered before this that unless the temperature of a fowl were lowered artificially, inoculation with the microbes of splenic fever would not produce the disease. From this he argued that, as the heat of the fowl's body was sufficient to resist the contagion, the bacilli themselves must be extremely sensitive to variations in temperature. He tried the experiment and found, by lowering the temperature of the flasks containing the cultures, he could prevent the formation of the spores. He then attenuated the venom of the splenic bacilli as he had that of the fowl cholera, tried it on guinea pigs, found they became sick and recovered, inoculated them with the bacilli of full strength, but with no result. Pursuing his experiments, he discovered that he could, by using vaccine-attenuated bacilli of unequal strength, cause any degree of sickness he pleased. In the early part of 1881, Pasteur agreed to hold a public exhibition of his vaccine for splenic fever, the animals to be supplied by the Society of Agriculture in Melun. The experiment was begun on May 5th. Pasteur inoculated 24 sheep, 1 goat, and 6 cows with 6 drops each of attenuated virus, and 12 days afterward he re-inoculated them with a stronger virus. On May 31st he re-inoculated the 31 animals with the strongest virus of splenic fever, and at the same time inoculated 25 sheep and 4 cows which had been vaccinated, as were the others. On June 2nd, over 200 people assembled at the farm to see the result. The 25 sheep that had not been vaccinated all died before that evening. The non-vaccinated cows had intense fever and great swellings, and could scarcely stand up. On the other hand, the vaccinated sheep and cows were in full health, and were feeding quietly. Pasteur had conquered splenic fever. Having attenuated the virus of these bacilli, Pasteur began a series of experiments to determine whether the attenuated virus could be intensified until its former venom was obtained. This he succeeded in, and thus discovered what is probably the key to the solution of the problem of the periodicity of epidemics of contagious diseases, such as cholera. In 1882, Pasteur's attention was called to a new disease, swine fever, rouget, which was ravaging the herds of swine in France. He found the microbes, attenuated them, vaccinated the pigs, and secured the most favorable results. He also discovered that by passing the microbe of a disease through an animal not subject to that disease, he attenuated it so far as its effects on another were concerned. It was in 1880 that Pasteur began his experiments in hydrophobia. Securing the saliva of a child suffering from the disease, he inoculated rabbits with it, and they died in 36 hours. He examined the saliva and the blood of the rabbits and found in both a new microbe, a minute disc having 2 points. He established by repeated experiments that hydrophobia is a disease of the nerves, that a portion of the medulla oblongata, or of the spinal cord, is very much more certain to produce the disease when introduced into the blood or placed on the brain than is the saliva. He succeeded at last in isolating the microbe, in making cultures of it, and then attenuating it, and in May 1884 he produced, before a commission appointed by the Minister of Public Instruction, the following results. Of 6 dogs unprotected by vaccination, 3 died as the results of bites of a dog violently mad. Of 8 unvaccinated dogs, 6 died after extravenous inoculation of rabic matter. Of 5 unvaccinated dogs, all died after inoculation by trepanning of the brain with rabic matter. Of 23 vaccinated dogs, not one was attacked with the disease after inoculation in any fashion, with the most virulent rabic matter procurable. During his long and busy life, Louis Pasteur has been honored after every fashion known to men. He has opened the gates of knowledge wider than they were ever opened before, and in his discovery of the germs of disease, and in his still more wonderful discovery of the possibility of attenuating those germs and converting them into vaccines, he has revolutionized all ideas of physiology. He is one of the greatest pioneers in science that has ever lived, and his work will make his name illustrious so long as men shall continue on this earth. The lesson of his life is the supreme value of experiment. For as was once said of him by Professor Dumas, Pasteur is never mistaken, because he never asserts anything he cannot show another man how to prove. End of section 29.